In this video, we'll talk about a powerful application of the mean value principle, or the mean value property implying harmonic, uh, namely the Schwarz reflection principle. So this basically says that if a harmonic function has certain symmetries, then it extends to be harmonic in a larger domain. So let U be a domain symmetric about the real line, by which we mean that the set of z's such that z conjugate is in U is the same set U. So it's uh, invariant under conjugation. And we also want it to intersect the real line. So now we set U plus to be U's portion in the upper half plane and U minus to be U's portion in the lower half plane. If we have a harmonic function in that upper portion, so maybe a picture helps. I have the real line, and then I have some domain symmetric across the real line. If I have that the limit of U of z as z goes to x on the portion of U on the real line, if this goes to 0, then we actually have an extension of U of the function U to the whole domain U. What do I mean? So I'll define this U tilde to be U of z in the upper portion, and it'll be minus U of z bar in the lower portion, and then it has to be 0 on the portion on the real line. And so the theorem says that this function is actually harmonic on the domain U. And notice this is pretty flexible. You don't have to have a domain symmetric about R. If I have some other domain, well, you can look at just individual portions, and if you have it defined here, and if it tends to 0 on the real line, then you can reflect it across and get it harmonic here. So, as I said, this is an application of the mean value property characterization of harmonic functions. So here was the mean value property again that we already proved. So if we have a continuous function on a domain, and if at every point it satisfies the mean value property, meaning it equals its average around small circles around that point, then U is actually harmonic. Okay, so how do we prove the Schwarz reflection principle from this? Okay, so by our assumptions, U tilde is continuous on the whole domain U. By definition, it tends to 0 as you tend to the real line, and this function is just a continuous transformation of U, and it tends to 0 as you tend to the real line as well. We also have that this function here, negative U of z bar, is harmonic on the lower portion. So you could just check that by taking the Laplacian or realizing that U composed with an anti-analytic function will be harmonic just as if you would compose U with an analytic function. So we have it harmonic in the upper portion and the lower portion, so it'll satisfy the mean value property in both of these open sets. So to prove that U tilde is harmonic, we just check the mean value property at points on the real line. So take an x naught on the real line in our domain and a disk around it that sits in the domain. And now we check the mean value property. So here's an integral of U tilde around along a circle centered at x naught. And I'll break it up into the portion in U plus and the portion in U minus, and we have explicit formulas for those portions. So it's just equal to U here, but then here I have negative U of z conjugate is the expression here. And so I'm going 0 to pi here, pi to 2 pi here. And I'll do just a change of variables with this piece. And I don't, basically, since this piece is e to the negative I theta, and we're going from pi to 2 pi, it's just as if we're going from, let's see, negative pi to negative 2 pi. And this actually keeps us in the upper half plane. And if you are careful with the signs, you'll see that we will exactly cancel out our earlier integral here. And so when you add these two things together, they cancel out and you get 0. But that's the value that we've assigned to u tilde at a real number. So the mean value property holds. So this gives an extension to all of the domain U. And so now let's talk about how you can extend this to analytic functions. So if I, again, have a domain that's symmetric about the real line as before, and if I have an analytic function on this upper piece, and the imaginary part of f tends to 0 as I tend to the real line, then magically f extends to be analytic on this whole domain, and it satisfies this reflection formula. And the miraculous thing here is that we're just assuming something about the imaginary part, and then automatically the real part, which is, this harmonic conjugate, it automatically extends to be harmonic. So that's one of the most powerful things about it. We have assumptions just about the imaginary part, but they automatically carry over to the real part. Okay, so let's look at the proof. Okay, so this function, this reflection function, is analytic in the lower half, and you could check that just by taking these d bar operations. If you do a conjugate twice here, it'll be analytic. Okay, then by the harmonic Schwarz reflection principle, the imaginary part of f will extend to be harmonic on all of u. And so we're doing this to the imaginary part of f, so that's a little confusing, but hopefully we can give somewhat of a coherent explanation. Okay, so now if I take a point on the real line, locally negative v has a harmonic conjugate, because we've already shown that harmonic functions always locally have harmonic conjugates u. I'm using negative v because it's the imaginary part, and you need to do this to get some of the signs to work out. Okay, so this function g here, so I have negative v plus iu will be analytic, and I've multiplied by a minus I to make it equal to u plus iv. So this function will be analytic near a fixed point x. Okay, but then g minus f will be real valued because g and f have the same imaginary part v. But this only holds in u plus intersect a neighborhood of x. But this is an open set, so this analytic function, which is real valued in an open set, has to be constant, so it's a constant real number. And we could modify the function u or modify g so that that constant is 0, because harmonic conjugates are only unique up to real constants. So we can guarantee that g is identically equal to f in u plus intersect this neighborhood of x. Now, this reflection of g across this neighborhood will still be analytic, but if you look at the reflection, I'll get u of z bar minus I v z bar. Well, the extension of v exactly has the property that when you reflect across the line, you have negative z v bar equals v of z. And so this reflection of g is analytic, and g minus its reflection is again real valued. And so you get that g is identically equal to its reflection across this line. And now we see that g is, since it's equal to its reflection, it's equal to this reflection of f on this lower portion. So now g is analytic across the real line, and it agrees with f's reflection. So that says that f extends analytically across the line using this function g. And then from here, maybe there's, if you were to be really careful, you would argue that since we have an analytic extension across all of these different points, you would just declare that f's extension across this line is given by all those different extensions, and they're unique because they have to agree above and below the line. And in the end, we get an extension of f across the real line. And the last thing we do is introduce some bells and whistles to the reflection principle, which is try to extend functions across analytic arcs. So I don't want to go too deep into this. Often books are semi-rigorous when it comes to this point. If you were to be really rigorous, you'd have to introduce a lot more kind of geometric machinery, I think. But let me give you the main idea. So an analytic arc is a smooth curve locally parametrized by an invertible analytic map. So locally, it looks like you're taking a piece of the real line under an analytic map and sending it into the plane. And so when you do this with an analytic arc, you have this analytic map that controls, you have sort of two sides to the curve, and it comes from an analytic map. So as I've written here, you have this analytic arc, and then you have one side of it and another side of it that just comes from the analytic map that you use. And so this is just supposed to be a local description of an analytic arc. So at every point you'd have to have a description like this, and maybe you don't have a global way of doing this. But then once you have this, you can locally define a notion of reflection, and if you're really careful, you can show that this is independent of the choice of phi. So given a point on this image of phi, the image of phi is u, given a point here, I can reflect it z star by taking the inverse map, which takes me back to this symmetric domain here, reflecting with a conjugation, as I've done here, and then mapping back over. And so this will send one side of the analytic arc to the other side. An example of this is just using the unit circle. So this fractional linear transformation, zeta goes to zeta minus I over zeta plus I. This sends the real line to the unit circle minus 1, and it sends the upper half plane to the unit disk and the lower half plane to the complement of the closed disk. And you can compute what the reflection in D is. So each point Z in the unit disk will correspond to one of these points under the map. And so I would map back to zeta, take a conjugate, and then again use the linear fractional transformation to get this point, which, if you check, is actually 1 over z bar, which is sort of a natural notion of reflection across the unit circle. So it takes a point here and reflects it across. So if it was r e to the I theta to begin with, it maps to 1 over r e to the I theta, because I do sort of a reciprocal and a conjugate will keep the angle the same, but it flips the radius. Okay, but one issue here is that this avoids the point 1, so you'd have to use a different map to cover the point 1, but in both cases you get the same reflection. So this is similar to something I alluded to here, that you can actually show that this, if you're careful with your definitions, that the notion of reflection doesn't depend on the map that you use. Okay, and so here's a cheap version of the Schwarz reflection principle for analytic arcs, where I have an analytic arc parameterized by a single analytic function. So assume phi is analytic and invertible, maps this disk of radius epsilon onto this domain U, and let gamma be the corresponding analytic arc, which is phi restricted to the real line. Now, if I have an analytic function on U plus, so that's just one side of the analytic arc, and generally you could formulate a reflection principle where F tends to another analytic arc as you tend to an analytic arc in the domain. I'm going to keep it simple and have F tend to the unit circle as Z tends to a point on this analytic arc gamma. So if F tends to the unit circle as Z tends to a point on this analytic arc, then F extends meromorphically to the whole domain U and satisfies this reflection formula. So we use the reflection across the analytic arc and the reflection across the circle and get an analytic function. Why is this a cheap version? Well, since it's parameterized by a single analytic function, you may as well just look at F composed with phi. And the analytic arc in the range is just the unit circle and has a simple geometry. So it's easy to say what it means that f of z tends to the boundary of the disk. You just say that the modulus tends to 1. A precise version of the statement that if z tends to an analytic, or that as z tends to an analytic arc, f of z tends to another analytic arc implies analytic extension. I have seen no book that has a very precise version of this. Some give just sort of intuitive explanations. Okay, but so as in the comment, to prove this, we may as well replace f with f of phi and assume that you have f mapping from the disk into the complex numbers, and it tends to 1. And basically the idea is you play with logarithms to get this to work out. So we fix a point on the line, and since the modulus of f tends to 1 as z approaches that point, there will exist a radius around there intersect with the upper portion of the disk where f is non-vanishing. So then on this neighborhood, we get an analytic logarithm of f, because it's simply connected, it's just half of a disk. And then the real part of log of f will always be equal to the natural log of the modulus of f. And this, since f tends to 1 in modulus, the log of that will tend to 0. And now this is a harmonic function. And so by Schwarz reflection principle for harmonic functions, log f of z will extend analytically across the real line to a function g, and the reflection is a little different here because it's the real part, but I encourage you to work out that this is the right thing. If I have an analytic function whose real part tends to 0 as you tend to the real line, then this is the right reflection for it. Okay, and then here's just kind of a sketch of the last bit. Capital F equal to the exponential of G will be an analytic extension of F, and it satisfies the right reflection. So you get that F will extend analytically along the whole real interval, and it has the right. And then we see that not just near the real line, we can extend f to be this function on the lower portion. And since now we're dividing, we may get a meromorphic function on the lower half somewhere, because if f has a 0 in this upper half, then its reflection will have a pole in the lower half, but that's okay. It's analytic across the real line portion. And so in this way, we reflect across and get a meromorphic function. So this is one easy version of a sort of general Schwarz reflection principle for analytic arcs. So F is tending. As you tend toward an analytic arc, F is tending to a different analytic arc, in this case, just the unit circle, and you get a meromorphic or analytic extension across the analytic arc. This theorem is really useful, though, for constructing all kinds of important functions like the elliptic modular function and functions with other symmetries.